All right, it says it's live. Hey there, welcome everybody. Welcome again to Astronomy Daily Live. This is just a casual, fun get together of friends each and every day at 2 hours UTC. We get together and we think and talk all things astronomy and science and space and whatever other kind of nerdy things we want to do. And yeah, so welcome. Come on in. Come on in. I'm I have a clear sky tonight, although it's uh, pretty humid, so I don't know how long my session is actually going to last. But I do have a number of stars to observe, doing some photometry with those, seeing how well my system actually works when I compare it to the big boys like Gaia. Um, see how well the measurements I can make of a selection of stars compares to those measured by like instruments like Gaia, which we professionals, we've sort of decided, that Gaia is a good standard. Um, and so yeah, at least one of the programs that I'm doing here is making measurements of those same stars, and then with software I can combine them, stack them up in various ways, and then do a thing that's called aperture photometry, and actually measure the brightness of those stars, and then compare my measurements to those of Gaia, and see if I'm able to basically get the same numbers. And what I'm seeing so far is that I'm getting numbers that are pretty comparable, somewhere around 30 or 40 millimagnitudes accuracy, and a precision around 10 or 20 millimagnitudes. So I'm both accurate and consistent with stars. So I'm fairly confident that my system is going to work at least that well, and of course definitely continuing to see if I can make improvements to that as well. And I'm moving into other realms as well. I'm going to be looking at a few variable stars, and going to be looking at, well, every other kind of astronomical object that there is, right? Galaxies, clusters, globular clusters, open clusters, planetary nebulae, gaseous nebulae, galaxies, binary stars, maybe even looking at the transits of exoplanets as well. That's sort of a tough nut, because the variability there is around 10 or 20 millimagnitudes. So, and that's about the sensitivity of my system at the moment. So we'll see how all that goes. But I see that Bobby has just re-popped into the panel here. Hey there, Bobby.
Hey, what's up?
Just sitting back, enjoying some dihydrogen monoxide. This is sort of a peppy molecule here just to keep me going. And look, wow, I'm actually already, I'm halfway gone already. So things are good. Things are good. I think the camera just defocused. So I'm gonna palm it here, and then, oh, there we go. All right, cool. All right. So yeah, so getting a little bit of a echo from you, Bobby. So
Yeah.
just FYI.
And I might have to reboot the computer because the connection is still being unstable.
Unstable connections. That's what these machines are. So, well, cool. So at sunset, I took all my calibration data, and this set of calibration data is some of the best that I've ever taken. So I've got a lot of it, and the signal looks really, really good. Took some really, really nice darks, some nice flats. So calibration was good. At 1:30 UTC, I looked at the clock, and I'm like, you know what? It's dark enough that I can actually do a skyline. Can I do a skyline in 15 minutes or 15 minutes or less? Well, that thought process took me about 5 minutes, and so at 1:35, I ran outside and did a sky alignment, and I was actually back in here at about 1:43. So sky alignment and focus took me about 7 minutes or so to do. So I've got a telescope and a CCD camera sitting outside right now, just waiting to be ran. Right. So yeah, I think things are good there. The only contention that I have right now is that it's pretty humid. It's probably about 70% right now. So things are starting to drip a little bit out there. And I've got one band of clouds that is sort of in the Phoenix area that is moving towards the southeast. I'm in southeastern Arizona, so these clouds are moving really, really fast. But at least the latest, and in fact, I'm going to pull up the latest satellite view here, and we can actually, why don't we take a look at that just for fun? Because this is one of the things, of course, that astronomers.
Hey, Art Radio, are you also streaming as well or no?
Hey there, ERRT Radio. Nice to see you in the chat. It's nice to drop by your radio show quickly. I wasn't there very long, but just so happened to get the email notification, and so I popped in over there just to say hi. So here's the latest satellite view of the southwestern United States, and as you can see, this is as of 1:45 UTC, so about 25 minutes ago or so. And so I'm down here in this area, had this band of clouds move through. Everything's moving from basically the northwest to the southeast pretty quickly too. So as you can see, this band of clouds has moved past me already, so that's all right. I've got this little clump of clouds here that is sort of moving towards me at a pretty good clip, but it's sort of dissipating, right? And then I've got all these things up here, which I don't think is going to be a big deal. So yeah, the only thing that I'm sort of worried about is this band of clouds, and I'm not too worried about it because if it moves through really fast, that is perfectly fine. Getting a lot of echo from you, Bobby.
All right. I will be definitely probably tonight get a headset since Tim's for quite some time he posted those headphones I was supposed to get from Tim, and I'm not sure what happened because he never posted the tracking information. So I might want to get I can get one at Walmart for about $5.
Okay. Yeah, I think that is probably a move in the right direction. Those headphones mean, that you don't have to have any kind of speakers on or anything else. That's what I'm doing too, right? I mean, I've got the headphones. So, and that just means that we don't have to deal with that at all. All right, so I'm going to stop sharing that screen and come back here,
So
and
our
I'm going to
news
look.
about getting the store data was take a look at that.
What's that?
Now you mentioned something about the store data. Did you got any pictures or data or something?
Well, not yet, but the telescope and the camera are all set up, waiting for me right now to go out and do that. Hey there, Tom. I see you in the chat too. Nice to see you there. So very
Welcome, Tom.
cool. Yeah. Glad you could come into the chat there. So yeah, this might be a little bit of a shorter live stream, just because I'm itching to get out, but it definitely isn't past astronomical twilight yet. Actually, you know what? It's probably really close
You can
to
do a
being.
Google search is what time is when is sunset time at your location. Just type in sunset and it should give you the sunset time at your location.
Oh yeah. No, I've actually I've got that kind of info, and so yeah. I definitely know that pretty close to astronomical twilight right about now. So yeah. Well, very cool. Glad everybody could come in, and yeah, let's think and talk astronomy for at least a little
It's
while
Tucson is
here.
TUCSON.
Mm-hmm. Yep. Sunset was about 5:33 local time, and astronomical twilight's about 7 o'clock local time. So yeah, I already looked all that up. So I try to stay on top of those kinds of things. So very cool.
So your sunset was about 5:30, right?
Mm-hmm. Yep. Indeed, it was.
Yeah, no, that's what I got too.
Yeah. And Tom just popped onto the panel. Hey there, Tom.
Hey, Cosmic. Sorry I'm late.
Oh, no worries.
Wrangling
No
some
worries.
stuff here.
Wrangling. Yeah. I know about those kinds of things. For sure. Hope everything's well over there.
Doing
What
okay.
is the difference between sunset and astronomical twilight?
Let's talk about that. You know what? Let's do that. There are actually several different twilights, right? So there is sunset, right? Which technically speaking is sort of a hard thing, but let's just say, okay, that sunset is when the sun is at an altitude of 0 degrees, right? It's right um, on the horizon, right? Well, from that point to when the sun is 6 degrees below the horizon, that's what's called civil twilight. Okay. When the sun is between 6 degrees below the horizon and 12 degrees below the horizon, that's what's called nautical twilight. And between 12 and 18 degrees below the horizon, that's called the astronomical twilight. So when the sun is 18 degrees below the horizon and lower, you're technically astronomically dark. That usually takes about an hour to an hour and a half or so. Depending on your latitude, sometimes it's even longer than that. In fact, if you live in the northern United States, technically you never get that dark. You're always in on the astronomical twilight, especially in the summertime. So yeah. But at my latitude, which is about 32 degrees north or so, I definitely get into astronomical twilight. It definitely is dark enough here. And yeah, I think that's pretty much where I am right now. So yeah, those are sort of the definitions of those kinds of things. Pretty cool. And
so
yeah.
here in Minnesota, is that the Norton sector?
I think it sort of depends on where in Minnesota he is. I think he said he was in southwestern Minnesota, so that's pretty far south. We'd have to actually work that out, but because of the tilt of the Earth is already 23.5 degrees, you have to actually add that to your latitude, and then figure out if you're actually seeing that or not. And so yeah, you'd have to do a little bit of math to figure that out exactly. So all right, well, cool. Let's
I've got a quick question. Are there
sure
circumstances where you'd use one of those twilights versus the others, or
I don't know.
the astronomical one makes sense to me, because that's an astronomer would want to know, like, when is it dark? Tell me when it's going to be dark, so I can go out and do this. The other ones, okay.
Yeah, I don't know if there is necessarily a use for the other ones. Being an astronomer, I've never had a use for any of the other ones at all. So yeah. Good question. Don't really know the answer to that. I guess the names themselves sort of imply a use, right? So civil twilight is sort of dark for city folk type, bright enough to actually be able to walk around and see the ground and everything. Nautical, again, maybe for the sailors of old, to be able to see things. But yeah, those actual terms, don't really know where those come from. Probably easy enough to find out. But yeah, for me, the only one I'm really interested in is the astronomical one, and that usually hour to an hour and a half or so is when we'll start seeing that. So and that sort of makes sense. 18 degrees is about, well, I'll pull it out here. One hour of right ascension is 15 degrees, right? So 18 divided by 15 is 1.2 times 24. Oh, did I do that wrong? Oh, yeah, is 1.2 hours of right ascension, which is what 1 hour and 12 minutes. So yeah, I usually think here from my latitude, somewhere around an hour and a half after sunset, I definitely know that it's dark. So and this time of year, sunset was about 5:30 p.m. local time. So I'm definitely past the astronomical twilight now, it being local time 7:20 p.m. here. So so yeah, definitely past astronomical twilight here. Nice and dark out there, but as I said, it's humid. So right after this live stream, I'm gonna run outside and see how much frost is accumulated on everything, and probably not yet, but it'll be a little bit of a rush, to get a couple of objects. Also want to try to get some images of M77. That's a galaxy over in I don't remember what exact constellation that's in. I'd have to look that up, but that's up at the moment. With the galaxy stuff, what I'm interested there doing is, not only getting some pictures of it, but I'll be able to do some radio profiles, actually plot the brightness versus position, see what that looks like. Look at the center of the galaxy, see how bright that is, actually make some magnitude measurements of that too. So yeah, lots of things can be done, with some pretty simple instrumentation. And what I have is definitely simple instrumentation. But I sort of back when I was a kid, I was part of a bowling league, right? And we thought for the longest time that if only we could have a really great bowling ball, because if we had a good bowling ball, then our scores would probably be higher than what they actually are. And so we'd always blame the bowling balls. It's just these are garbage ones, or they're cheap, or anything else, and that's why our scores were never as high as they could be.
I'm gonna be right back.
Okay, yeah, you are Robot Bobby for sure. So there he goes. Yeah, yeah, he's having technical difficulties, but yeah, we thought that it was the bowling ball that was causing our low scores, and if only we could have better bowling balls, then our scores would be higher, right? And of course, that is definitely not the case, right? Now, I don't know who these days who are sort of the top professional bowlers and stuff, but at least back in my day, it was Mark Roth, Earl Anthony. Oh, what was the one guy? I forget his name now, but I can say probably with pretty high confidence that somebody like Earl Anthony, right, could go to the, they always have bowling balls there at the bowling alley, right? I'll bet you that he could walk up to any of those bowling balls and probably get a pretty high score with any of those. Now, at that level, right, having a good bowling ball actually does help, right? Because it has certain parameters. The bowling ball itself is made a certain way. It's got things inside where the weights are offset, and all kinds of things, right? The material that's used, the kind of oil that's used on the lane, how the oil is laid out, those kinds of details make a difference at that level. But at the same time, somebody like that could probably still score really, really well, even with sort of a mediocre kind of a bowling ball. And the same thing goes in terms of doing astronomy and doing science, right? Don't fool yourself into thinking that you have to have, top of the line equipment and all the bells and whistles and all these great things. If you're a good bowler, you're going to score high almost regardless of what kind of bowling ball you use. And it's the same thing when it comes to professional astronomy, right? If you're a good, really good at doing astronomy, then the equipment almost doesn't matter. Almost. So, as long as, with bowling, right? As long as the ball is round and as long as it's got some holes in it, so you can grab it and roll it down the lane, you're probably going to do really, really well. And that is definitely the case when it comes to astronomy too. So don't think that you have to have, top of the line equipment. Get something that is, at least decent, and you'll do really, really well. Really, really well, right? I mean, I'm seeing 20 or 30 millimagnitude accuracy, and 10 or 20 millimagnitude precision, which is really, really, really nice, and it can actually be made better too. All right, Bobby is back. Bobby, are you there?
Hey.
All right, we'll see how this goes. Did you do a reboot?
Yeah, I just had to disengage a tap so it could be a little bit more stabler.
All right, cool. Yes, we want stable potatoes here. Stable potatoes. So for sure. What I thought that I would do tonight, last night, we were looking at the JPL Horizons website, where you can get an ephemeris for any object in the solar system, right? Getting a little bit of echo from you, Bobby, too. Sorry about that, but I'm going to whine and complain about it.
Turn it down a little bit more.
Yeah, okay. Appreciate that. So, but one of the things that I sort of blew over was they had listed sort of a detailed explanation of all these parameters that you can set and then see as part of the output. So what I thought that I would do just for a little while here, like I said, I think I'm gonna keep this a little bit short tonight because I'm itching to get out, but I definitely like to do this too and want to do this too. Let's look at some of those definitions and sort of see if we can make some sense out of them.
Before you start that, could you tell us what an ephemeris is exactly? I'm not sure I know what that means.
Okay, yeah, absolutely. We can let me get this set up and we can do that. I'm watching clouds at the same time that I'm doing this. So I've got myself over at the Horizons website. So I'm going to share my screen. And in fact, before I do that, let me check the chat really quick just to make sure that we're good. Yeah, RT, I've got a 8-inch Celestron, so it's just a different mount, right? It's not exactly a Dobsonian mount. Wouldn't call it an equatorial mount either, for sure. It's just an alt-as mount. So, but not exactly a Dobsonian. I actually do have a Dobsonian. Well, I did have a Dobsonian, but that's for my 10-inch, which I've actually modified now, so it's not even a Dobsonian anymore. It's a German equatorial mount. So, all right, cool. I'm going to share my screen. And so, an ephemeris is a table of data that shows you position versus time. And that position can be a lot of different kinds of positions, right? It can be like a vector distance versus time, or it can actually be like a position in the sky versus time. So
Earth radio, but for the beginner or the one getting into it, would it be good to get the kind you had?
Yeah, you know, the C8 is a great overall scope, not only for beginners but for pros. So I mean, it really covers a really wide range, and that's why, you know, I mean, really, you know, to do science, you don't really have to worry about telescope size or you know, quality of the camera. All these things can sort of be dealt with, and you know, as long as you're not, you know, going to the dumpster, right, in the back of the store, you know, and pulling out, you know, your plastic CCD, you'll do really well. It's really amazing, you know, how well these things work for you know, not much for sure. So all right, so an ephemeris is basically that. It's just position versus time, and you can sort of define position in lots of different ways, right? Like I said, one way is to define just vectors, right? You know, just an X, Y, and Z distance versus time. That's an ephemeris. If you want to do right ascension and declination versus time, that's also an ephemeris. So yeah, sort of in a nutshell, that's what that is. Pretty easy.
Okay, thanks.
Yeah. So let's dive in here and see if I can find what we were looking at the other day. Is it this one? I'm trying to remember now exactly what we were looking at. Plain text. Maybe it was under observer table. Let's set that and then go back to this. And here we go. Observer quantities are described in Horizons documentation. So yeah, it was just all this stuff, right? There's so much here that I sort of wanted to look at, you know, these things anyway, right? So let's dive into this a little bit and see, you know, because these are all parameters that you can set and view, right? This is kind of an interesting thing. Let's go for, yeah, I don't know if that would make any sense to an ephemeris or not, to have an observer location on the Earth and a target body be the Earth. I don't know what that would do in terms of showing an ephemeris. Huh. All right. Well, I'm not going to look now, but yeah, you know, there's all these other parameters that you can do. Well, you know, let's do this anyway. Let's take Mars. Let's look at Mars, like that, and let's do. Yeah, we can do it over the course of a day, right? So I set these yesterday, so I'm not going to go through all these again, but let's just look and see what this ephemeris looks like. And I will zoom out again so we can sort of see the whole thing. So a bunch of different parameters here, right? Here's the date. Two different ways, right? Here's sort of the normal way that we see a date and a time. This is the Julian date. So here is the right ascension, declination. So this is how much it's moving, and I think it said it was in arc seconds per hour, right? So this is the right ascension motion. Here's the declination motion. I think this was the magnitude, the apparent magnitude. SBRT, I don't remember exactly what that is. Let's go down here and find out. SBRT, okay, so that's just the brightness per square arc second. So yeah, I guess that's an interesting value for some reason. Angular diameter, and that's probably in arc seconds as well. Yep. And here's the range. So how many kilometers it is away from the observer, which in this case is me. I've put myself on top of Mount Graham, which is just to the north of me here at the Large Binocular Telescope. And then this is just the range rate, right? So it looks like it's moving away from me at 14.5 kilometers per second. So that's Mars. So as you can see, you know, each day, right? We're looking at this each day. It looks like it's moving, and that's because we're moving and it's moving. So pretty cool. All right, so that's at least what these quantities are that I just sort of chose here, right? But there's 43 quantities here, and then there's all this stuff too. I don't know if they've got an explanation for all this or not. A lot of this, you know, is pretty self-explanatory. But yeah, let's dive into the documentation here and just sort of see what they have to say about all this stuff. Let's see, gotta find the start of it here. All right, so general definitions. I'm going to zoom in a little bit here. We can do that. It's a little big. Here we go. Okay, so right ascension, of course, declination, geometric coordinates. So the instantaneous position of a body at a particular instant, referred to the equator and the equinox of a particular reference frame. Yeah, I figured that this was probably going to get complicated really, really quick. So, yeah, I think I'd have to dive into this a little bit more to really know what that means. So I'm gonna move on a little bit here. So the astrometric coordinates versus the apparent coordinates. The apparent coordinates, I think, basically take into account the atmosphere, right? The atmosphere refracts light a little bit. You know, just like when you put something like into a glass of water, it seems to be in a different place. Same kind of thing happens with air, just a little bit more subtly, right? And I guess it also has to do with these inertial frames, which is a little more complicated than what I want to get into, mainly because I just don't remember what that exactly means. All right. Okay, yeah, and here's actually the refracted coordinates too. So yeah, lots of different ways. You know, I mean, if you want to very, very accurately determine where something is, you have to say, okay, well, what does that mean, right? You know, with respect to various forms of distortion, right? So that's what that all is, I guess. Azimuth, elevation. So that depends on your local location, right? You know, you know, something that is, you know, right at the zenith where I am, isn't going to be at the zenith at the same time, you know, where Tom is or Bobby is, right? Those positions are going to be slightly different. And that's, you know, mainly because, you know, we live on this sphere, right? That sort of uh, um, is a good argument for, you know, the fact that we are on a sphere. Let's see. So small body refers to a comet or asteroid. You know, what would really help is if we had this going too. So where's small body on this? It's kind of strange that they wouldn't do it in order, but oh, maybe that's what this is up here. Okay. So a small body is a comet or an asteroid. Trajectory is numerically integrated on demand from an initial set of previously statistically estimated orbital elements. Typically, no cartographic coordinate system is available for these objects, but there's a growing number of exceptions. Okay. Major body refers to a planet, and that, I guess, is... Again, I'm not seeing like a selection for major bodies. Okay. Well, let's keep going here. Oh, okay. Maybe... Am I looking at this? I thought that this was going to give a explanation of each of these entries, but now that I'm looking at it a little bit more, maybe this is talking about other things. I guess so. All right. I thought that this was going to sort of explain all the options there, but this is getting into more details in terms of, you know, actually how to use the site. So, No. Yeah, this is getting a little further out than what I was thinking that we could go here. Let's see. Definition of observer table quantities. Maybe this is getting a little closer. Time, solar presence, statistical uncertainties, specific quantities. This looks like more like what we're doing here. Okay, so I think this follows this list, right? Astrometric R-index, apparent R-index rates. Aha, yes. Okay. Well, like I always say, all you folks are coming along this journey with me, so you know, you get to see me stumble along a little bit here. That's how it is. That's how it is. No guarantees that this is ever going to be smooth because you know, I'm doing it, so that almost guarantees it's not going to be smooth. So okay, here we go. So astrometric right ascension and declination of the target with respect to the specific observing site. So again, you know, with respect to a particular coordinate system, which they're calling ICRFJ 2000, which is going beyond what we're going to be talking about here, at least right now. Okay, so yeah, apparent, right, can have 3 different meanings. So for Earth-based sites, it's the apparent coordinates are with respect to a true equator and Earth equinox of date coordinate system. Okay. So an equinox of date coordinate system, I think, is saying, you know, where do we define the 0 point of the equinox? And for us, I think that is the vernal equinox to the spring equinox. So where that is in the sky, that sort of defines, you know, 0 hours UTC, or I'm sorry, 0 hours right ascension. But there's, yeah, light time that has to be taken into account, gravitational deflection of light, stellar aberration, which has to do with the motion of the Earth itself, and refraction. So non-Earth sites without rotational models, like spacecraft, I guess. So there's another possibility, and then non-Earth sites with rotational models. So I would think that this would be like, you know, if your observer is on, you know, like a different planet, say. I guess, yeah, that's sort of how. So how I would read that. All right, let's see. Right, so angular rates, and it's computed like that in arc seconds per hour. So yeah, it's, you know, it's a little bit of math, but no big deal. I mean, it comes down to, you know, how is this object moving in both right ascension and declination in arcseconds per hour. So of course the azimuth and the elevation, depends on where you are on the planet. And again, it looks like they compensate for light time, gravitational deflection of light, stellar aberration, which again is Earth motion, and also precession and nutation. So how not only how the Earth is moving through space, but how its rotation is wobbling in various ways. So yeah, to get extremely accurate positions of things, you need to take all these things into account. It's crazy. It gets really crazy really fast. So azimuth and elevation rates as well. So just like right ascension and dec, you can do that in arcseconds per minute. So X and Y satellite offset and position angle. Is that the next one? Satellite XY and position angle. I have no idea what that is. Let's see. Satellite differential coordinates with respect to the central body along with the satellite position angle. Differential coordinates are defined in right ascension as this big long equation and dec as that long equation. Holy moly. Non-lunar satellites only. Huh. Sat PANG is, oh, what's CCW angle? Oh man, this is starting to fly over my head really quick. Yeah, not quite sure. I'm gonna have to think about this one a little bit. That's kind of a tricky one. I'm not quite sure what SatPang is. Sounds interesting. Don't know what it is. Dang. There's way too many things I just don't know. Gonna have to figure that one out. So local apparent sidereal time. That's kind of a neat one. That's if you go outside and find the North Star, right, the North Pole, and sort of note that location, right, and then if you look straight up, right, straight up at your zenith, and note that location, and then draw a line between the North Pole and the zenith, and sort of extend that all the way down to the south and all the way north, right? That's what's called your meridian, and it's just your north-south line. Well, the right ascension of your meridian is what's called your sidereal time. So it's just the right ascension of your local meridian. And of course, that's always going to be changing because the Earth is rotating and things are moving. So that's kind of a neat measurement of time, is sidereal time. Most observatories actually show that up on their screens, right? So you always know exactly what the right ascension of your meridian is. Because say that you've got the telescope open and you're looking around, and your sidereal time is, say, 2 hours 30 minutes, right? Well, if your object is at 22 hours 30 minutes, it's not going to be up in your sky, and you know that right away. So that's kind of a nice thing. So pretty cool. Sidereal time, air mass, and extinction has to do with again, you know, where your telescope is pointing, and air mass has to do with actually how much air are you looking through, right? If you're looking straight up, again, right to the zenith, then you are looking through an air mass of 1, sort of by definition. But as you change your angle, right, and look lower, the amount of air that you're looking through is actually going to get more and more and more. At the horizon, your air mass, I think they define your air mass as infinity, I think, or you know, really, really close at least, right? So yeah, that's kind of a nice thing. Extinction has to do with either the brightness of your target, or how the color of your target changes, you know, depending on where you're looking through the atmosphere. It gets really, really complicated really, really fast. Yeah. But these are parameters, you know, that you can look at and you know, be aware of at least. Visual magnitude, that's an easy one. Surface brightness. Not quite sure why they would include surface brightness. It's the average airless visual magnitude of a square arc second of the portion of the apparent disk. Okay, I gotcha. So yeah, you know, surface brightness has a lot to do with sort of extended objects, right? Like planets, satellites, asteroids, comets, that kind of stuff. And you know, they actually give a little explanation here too. If you want to go through all the math, there you go. I think at some point, you know, we probably should, because I mean, it sort of looks complicated. It really isn't, but I would want to spend a little bit of time, you know, preparing. Don't necessarily want to do this off the cuff, because you know, I don't want to waste anybody's time. I definitely don't want to waste my own trying to figure all this out on the fly. So yeah, we'll come back to that one. So yeah, in some cases, just portions of a target are lit up by the sun. You know, you can think of like the moon, you can think of Mercury and Venus for sure. I think some asteroids to a certain extent, but I think that's probably about it. I think when it comes to something like Mars, I don't think that we necessarily see any kind of phase with Mars. Maybe a little tiny bit, but not very much. Defect of illumination. I've never heard of that before. It's the angular width of a target circular disk diameter not lit up by the sun. Have to think about that one a little bit. Wow, you know, there's a lot of parameters here. I think there were something like 43 of them. Wow, okay. All right, well, I'm sort of looking at the time and noticing that it is, wow, it's 3 hours UTC. I'm sort of wondering, maybe we should pick this up again later and you know, maybe I'll go through this a little bit more too, just so, you know, I mean,
I cannot believe every time you say you're going to do a short stream, it's always going to be like an hour more.
Yeah, yeah. Well, you know, that's what happens. You know, once I get going, it's hard to stop. So,
well, you should get out to that telescope waiting for you.
yeah, I'm sort of thinking that maybe that is what I'll do. I definitely want to take a look at this a little bit more. You know, not only for, you know, the live stream here, but, you know, mainly because I sort of want to know a little bit more, um, more here too. And, you know, there's so many tangents, right? I'd like to understand a little bit more, you know, these reference frames and stuff too. You know, it's things that I've heard a lot about, but, you know, have never really dove into, you know, even shallowly. Yeah, I think this is maybe I'll do a little bit of homework here, and we can definitely continue this, because, you know, there's a lot of you know, nice topics here, and a lot of tangents, right? You know, that we can sort of go, well, what does that exactly mean, right? And, you know, we can get into this math a little bit too. Like I said, there's nothing really complicated here. It's just a matter of understanding what all the variables are, and then you know, trying to understand, you know, once we plug in, you know, some numbers here, see what the results are, and and see what all that means. So, yeah, let's continue this next year. We're going to have to wait a whole year, though, to be able to do that. So I hope you don't mind. But yeah, I think I'll pick this up next year. So yeah, this is the last live stream, and technically speaking, in terms of UT, this is the last day of 2018. So wow, absolutely amazing. So yeah, the next live stream will be happening on January 1st, 2019, which is just a little less than 23 hours from now. That's totally amazing. So very cool. Time is flying by, so I must be having a lot of fun. All right, well, New Horizons, going by the asteroid in a little less, well, actually a little bit more than a day or so. We've got a Chinese moon lander that I think is going to be landing on the far side of the moon in the next day or so as well. OSIRIS-REx is going to be parking also near an asteroid in the next day or two. So lots of cool things happening out there for sure. So all right, you guys, yeah, I think I'm going to get out to my scope, make sure that the frost hasn't yet taken over that system. Hopefully get, you know, a little bit of data tonight. So yeah, I think I'm going to get out of here for now. All right, so take care, everybody. I will see you next year. Incredible. Thanks for all the time you spent here, coming in here. Let me check the chat again really quick, just to make sure that I'm not missing anything. Uncle Bill, awesome, very cool. And yeah, nerds like to talk all the nerd stuff, and that makes the time fly. So all right, you guys, take care, and yeah, I will see you in a little less than one spin of this Earth, jumping into next year, 2019. Amazing. All right, take care, everybody. I'm out of here. Bye.
There.